Good afternoon everyone and welcome to Science Snippets. I'll just remind you all that you can always check our website for the schedule to find out who's speaking next, and you can also watch previous presentations up there. So without further ado, we'll enter our first talk. So first of all we have Pete Betts. Pete is an Associate Professor in Structural Geology here in the School of Earth, Atmosphere and Environment, and he's also our Associate Dean of Research Training in the Faculty of Science. In addition, Pete is a director of a consulting company, PGN Geosciences, who specialise in structural geology, geophysical modelling and interpretation, and 3D modelling. His own research interests include geophysical analysis of Proterozoic basin systems, Proterozoic tectonics and plate reconstruction, and geodynamic modelling and geophysical interpretation of modern tectonic settings. He is currently undertaking research in the Red Sea, modelling accretion at convergent plate margins and constraining the architecture of the Australian continent. On another note, Pete recently won the ultimate prize, Bogan Prize at Bogan Bingo, a prize that he is very proud of. So that's something to ask him about over pizza lunch at the end. If you'd like to hear more about Pete, you can also find him starring in one of the faculty's really excellent science stories on YouTube. Today he's going to start us off on a bit of a theme of evolution by speaking on understanding the evolution of the Earth. Please welcome Pete.
Thanks, Kay. So when Kay asked me to do a science snippets, I decided to pick the most outrageous thing that you could try and present in 10 minutes, and I've failed abysmally, but I'll have a crack anyway. So we live on a planet Earth, and we actually, when we look at ourselves as geoscientists, we really don't know much about it, and there's actually really good reasons for that. And I was at a conference a few months ago, and a really famous geodynamic modeller stuck up this graph, and I think it summarises Earth sciences in its most simplest manner. What don't we know about its evolution? And in the end, it falls down to the vertical and the horizontal axis on this graph. The horizontal axis basically shows us the rock record, which geoscientists have been accessing since the onset of our discipline about 400 years ago. And the rock record really only allows us to look at the skin of the Earth. And that's the first couple of 100 metres. Maybe we can stick some drill holes down to a couple of kilometres. And we basically have to read those rocks and try and understand the evolution. And of course, there's a time factor with that. And that clock up there tells us about that time. And if we were to put Earth history into an hour, pretty much all the things that we value and think about on Earth, life, modern tectonics, happens in the last hour, back to about 3 hours, and everything else is kind of a bit more esoteric and difficult to understand. Okay, so as we go back through time, the rock record gets sparser, it gets harder to read, and it's a bit like God giving us a jigsaw puzzle to sort out, and then he takes some of those pieces away, he colours them in a different colour, and somehow you're supposed to sort it and unravel it. On the modern Earth, we still get to look at that skin and assess it, and we've got wonderful data sets that tell us about our Earth, but we're actually getting a snapshot of the Earth today. And we use that data set the data sets we use are basically geophysical data, and that allows us to image the Earth. But the limitation of that data set is it's telling you about now, not about the past. And when you look at that, the rest of that graph in space and time, you can see that 99.9% of that graph is blank, and that is stuff there's no data available, so we have to think about how we try to understand the Earth. So why don't we understand more about the Earth? I've kind of summarised that. We can image the modern Earth using geophysical methods. This is just an image of basically the ray paths of seismic waves related to an earthquake that happens near the surface of the Earth, and we're able to read those seismic waves, and that tells us about the structure of the Earth. This is stuff that we would teach at first year on the structure of the Earth, and from that we know that there's an inner core that's solid and made of iron and nickel. There's an outer core that's liquid, so certain types of seismic waves can't pass through that. Then we have a mantle, and then we have a thing called a lithosphere, which is basically the rigid shell that our planet exists on. So, you know, when someone says, well, how deep have we drilled? Well, it's about 12 kilometres, guys. So when we stuck our longest hole in, that's Kola, which is that top image there. That's a Russian drilling program. They've pulled the pin in 1989. They got to about 12K. It took 40 years to get there, and actually didn't find anything that's too amazing. The other way we can take, it's a big investment for not much information. The other thing that we can do is sometimes volcanoes can spit out rocks from the deep earth. And that tells us something about the rocks down to about 600K. So there's ways to get to those things, but from some sort of geological perspective, but it's actually not telling us much, because for a planet that's 6,300 kilometre radius, the top 300 or 500 kilometres is not very much. We have a plethora of geophysical data sets that we use, and I'm not going to talk you through these, but the one on your left is basically a map of earthquakes, and it tells us a lot about the plates, the geometries of the plates, and what those plates are doing and what their edges are doing. But it's not telling us anything about the past, it's telling us about today. The area of expertise that I have is kind of these middle data sets. I interpret the Earth's gravity and magnetic fields, and I look for things like crustal architecture, and there's multiple scales. These things, the magnetic data set tells you something about the structure of the Earth down to about 25 kilometres depth, and then the temperature gets too great and you basically start to lose the magnetic response. And the gravity data tells you, really images stuff down to about the thickness of the crust, about 35 to 100K, depending on where you are on the planet. Over on this side is two other data sets. The top one there with the bright colours and the black and white lines is seismic reflection data, which can image the crust, and the colourful map is basically a map of electrical conductivity. Again, shallow information. And then we have seismic tomography, which uses these seismic waves, and what we basically do, we have a theoretical model, and we test the seismic response against that theoretical model, and if there's any perturbation in that theoretical model, it tells us something about the change in the wave speeds in the crust and the lithosphere and the mantle, and then we can make some inferences. And the sections through here is depth, and you can see what we're imaging there is basically the response in the mantle to the Hawaiian hotspot chain. Again, this stuff is really telling us about shallow features, except for the seismic tomography data. When we step back through time, it is starting to become a bit about art and imagination. I call it jigsaws. There are some quantitative information that you can use. So we use paleomagnetic data, which is basically looking at the ancient magnetic field and trying to figure out where continents were with respect to the North Pole. And then when we start to do that for multiple continents and start to overlap them, we can join the continents together. Okay, it's really effective to do this in the last billion years, because we have really good data sets that allow us to do this. As we step back further through time, it gets harder and harder. And here's a couple of examples of that. So here's this map here basically is showing you the North American continent, or we call it Laurentia in geology speak. And basically, when the red and the green paleomagnetic poles overlap, it's telling you that's when they're together. So if you can date the rock and get the poles to overlap, it's telling you when they're converged. This sort of information, we use this to basically map out the distribution of continents through time. Once we use that paleomagnetic data, we can grab geological information and join some of the dots. And this is this image here. It's a paper that we've got in press in my research group. And it's basically figuring out how the Australian continent has formed together using geological data. And then we've taken the coarser paleomagnetic data and related that to the bigger picture. And basically, we use the combination of the rock record and paleomagnetic data to kind of unravel the continent. So, in the ancient past, it's a little bit about making it up based on the data that you've got, and there's some quantitative data that also helps us. But the quantitative data is very coarse and sparse, and we actually need to be able to date the rock, and we need to be able to figure out what the paleo pole was at that time. So I want to jump forward into looking at rocks today. Sorry, not today. Rocks we're standing on. So we're standing on here in Melbourne, what we call a microcontinent, which is a very small piece of continental crust that was once floating out in an ocean, and it collided onto the edge of Australia. And if you go to a geological conference and you want to hear a bun fight, go and listen to the Geological Survey of Victorian guys give a talk, and then go and listen to the Geological Survey of New South Wales guys give a talk, and they can never agree on anything. And the part of that was it's because their rocks are very different, even though they should be well connected because they're part of the same geological province. And a guy called Ross Cayley, who's from the Geological Survey of Victoria, has started to develop a model whereby he's been able to unravel and reconcile all the differences in these fights that have been going on for 35 plus years. I'm not going to talk you through the details. Ross takes more than an hour to explain it to people, and he speaks at 1 billion words per minute, so to explain that. But the pretense of the model is that this microcontinent comes in and everything starts to wrap around the edge of that microcontinent, okay? And so one of the things with this is that this was a completely outrageous model when people started to propose it, and people were not very happy about this. But basically what we did was we had a plate straight edge, this microcontinent collided, and then it's this subduction zone, which is where oceanic crust basically gets recycled back into the interior of the Earth, started to migrate back around the edge. And this is pretty much a picture from that Ross provided for this paper that we've recently published in Nature on this topic. And the issue was, how is this possible? At the same time as Ross was developing his model, let's see if we can go forward, Louis and I were working on continental accretionary dynamics, and Louis had basically developed code that was able to do these sorts of models in 3 dimensions. And this was the first group that was able to then take these models and put it into supercomputing space, and then we were able to do much more in that space. And the types of models that Louis was developing was doing this. And I'm just going to stop at some point. I'm going to pause it there, and you can see at the tip of this microcontinent, as it turns out, this is the supercritical thing and the game changer in terms of understanding how the edges of continents evolved. It was critical because it was the thing that had the perturbation that allowed this edge of the plate to migrate around the edge. And we did a road tour of this through North America, and I never felt more isolated, and I was starting to feel like I was well, I wasn't a scientist, so I was given a pretty hard time about it. And but the more we showed it and the more we looked for these solutions, we found it. So what happens is basically the plate keeps migrating this way, but the subduction zone actually migrates around the edge of the plate and basically creates a new ocean that opens up in this. Now, this is a complicated tectonic environment that I'm not going to talk about, but the drivers for this is basically, you can see this little white gap in here. That's a hole in the subduction zone, and basically allows mantle to flow horizontally through that hole, and it starts to push the plate sideways and back around the edge. The exciting bit about this was, for the first time, we understood how these things accreted onto the edge, but also how these plates and subduction zones re-establish themselves after a period of congestion and instability at the edge. The amazing thing was these models started to show that when we start to tack things onto the edges of continents, they weren't just going on the edge and the subduction zone was initiated, but it was actually embedding the continent into the overriding plate. So how long have I got now? 2 minutes, excellent. Here's another one. I'm going to get through this, here's a different view of it. But basically you can see the subduction zone stops, and you can see the subduction zone ripping there, and the mantle will flow around the edges as shown in this figure and starts to compress this back. Now we were like, oh, this is amazing when we did this, because it explained a whole bunch of observations that we never really understood before. But the issue was, did we see anywhere on the modern planet where this was happening? And this was the criticism that we had from almost everyone that we presented this to. And of course, once you see something with different eyes and a different point of view, you start to see it everywhere. So we saw it at multiple scales. I'm going to highlight this on this picture. And this is basically a map of global topography and global bathymetry, which is the topography of the seafloors. And so we start to see these patterns all over the planet. At the scale of the globe, India is a microcontinent. It's one of the world's biggest collisions and one of the biggest collisional events on the planet. But what essentially has happened in that time is that this was once a very straight subduction zone that basically went through here. The ocean was called Tethys, And basically it was when Gondwana disassembled, which is a large continent, and collided with Eurasia. And you basically had a continuous mountain range from Spain pretty much all the way to New Zealand. Okay? And so what happened was, when India, which was one of the final stages of this mountain forming event, collided, the subduction zone that existed in through Southeast Asia basically started to retreat, and today it's actually migrating backwards like this and trying to wrap around India. So that's a very large scale example of the phenomena that I was showing you guys. And on a small scale, we also see those bendy shapes through here. This is the Band of Arc, basically Australia, which I describe as a hammerhead stingray, with Papua New Guinea here, and then it basically you have a little a small ocean through here, and the opposite through here, and then there's the stingray bit of Australia. Basically, when this hammerhead collided with this plate here, the subduction zone that was straight started to migrate around the back of the hammerhead. Now it stopped because it wasn't oceanic crust all the way through there. And on the modern, and even a more modern example here is up in Taiwan. Here's the edge of the Philippine Sea here, and it's actually collided, and this subduction zone here is migrating backwards this way. So I don't want to dwell on anything more to say, except for to say that the reason why I showed you these geodynamic models is that the future of understanding that space that we don't understand about the Earth has to come from these types of models. They have to get more complicated. They have to link the mantle dynamic with the lithosphere dynamic, and we have to start doing that pretty much on a globe rather than on a Cartesian surface. But these geodynamic models are really providing insight into how we understand the Earth, and I think my time is up. Thank you for listening.